Isotopes. Nuclei with the same number of protons are the same element. But when they have different numbers of neutrons, different atomic masses, they are called isotopes. So, same number of protons, different number of neutrons. For many elements, there are a few different isotopes that occur naturally. Isotopes of a single element mostly have the exact same chemical properties because chemical properties depend on the electron structure. And isotopes all have not only the same number of protons, but also the same number of electrons. So they're pretty much the same chemically. There's some difference, but for the most part they act the same chemically. However, they can have quite different nuclear properties. For example, one isotope could decay in 1 microsecond. That's the total amount of time that isotope would live. An isotope of the exact same element but a different number of neutrons will never decay. It will stay forever. It will never break down into anything else. But the chemical properties, again, which depend on electrons, will stay the same. Natural abundance is the percentage of an element that occurs as a certain isotope in nature. So if you have a natural abundance of 99% for one particular type of isotope, that means if you found all of the different isotopes of that element on the planet Earth, 99% of them would be that particular isotope. Many isotopes that do not naturally occur, so they're not part of the natural abundance, can be created in the laboratory with nuclear reactions. There's a lot of numbers on this slide, so let's take this one slowly. Atomic mass. We don't talk about kilograms because they're way too tiny for that, and again, physicists somehow take very simple units and make all kinds of different ones to, specifically to work in their field, but to somebody coming in from the outside, it looks horribly confusing. But let's look at this thing. Unified atomic mass units, abbreviated U, and some textbooks you'll see it abbreviated AMU, but we're just going to call it U here. And we're going to say that a neutral carbon atom that has 6 protons and 6 neutrons has a mass of 12.000, etc. atomic mass units. Okay? So, if you were then to calculate the actual mass of the protons and the neutrons, multiply 6 times the mass of the proton, 6 times the mass of the neutron, which is slightly heavier than the proton, you will find that one atomic mass unit, here's a definition right here, is equal to 1.6605 times 10 to the minus 27 kilograms. When we work in nuclear physics, we need a lot of significant figures because, well, one thing, we can measure that well, and also a lot of the effects only come out at the 3rd or 4th decimal place. So that's why you're going to see a lot of numbers to the right of the decimal point. Now, this isn't good enough for us. We want to represent the mass in other types of formats. So we use Einstein's E equals mc squared, and we also have another unit of energy here. Joules is what we were taught first semester in mechanics. We now have a thing called the million electron volts, so 1 MeV is 1.602 times 10 to the minus 13 joules. We take Einstein's equation, divide through by the speed of light squared, see the c squared there, and then I plug in the mass of an atomic mass unit in kilograms. That's this guy right here, comes down to here, and you can see we have another decimal point here. We put a 4, another number to the right of decimal point, times the speed of light squared, divided by a conversion from joules to MeV, and we come up with an atomic mass unit is also defined as 931.5 MeV per c squared. The reason we do that is it helps when we talk about different equations, different ways of expressing nuclear physics. So, we have 3 ways to talk about mass at the nuclear level. We have one atomic mass unit is equal to 1.6605 times 10 to the minus 27 kilograms, which equals 931.5 MeV per speed of light squared. Hopefully this slide will make things a little clearer from the previous one. we talked about three ways of representing the mass of an object, of these electrons, protons, hydrogen atoms, neutrons. And we're actually calling it rest mass, which is the mass of the object when it's not moving. And the reason we talk about that, when you get into relativity, the mass changes, but we're not going to talk about that in this section. You can see the rest mass of the proton is slightly less than the rest mass of a neutron. So here's kilograms. We're very comfortable using kilograms. We've been doing it all year. In atomic mass units, that's the U here, you can see where a proton is a little larger than one atomic mass unit. The neutron is larger still, okay? And then over here you have the third way of representing mass. So these are just three ways of telling you what the mass of these particles are. And you can see how massive the proton, hydrogen atom, and neutron are compared to an electron. An electron is very tiny, 0.511 MeV per c squared. And a good way to remember the mass of an electron, the rest mass of an electron in these units, is on highways now you'll see signs saying dial 511 for highway information. I'm not sure if they copied that off of the rest mass of the electron. Probably not, but it's a good way to remember it. Because the atomic mass unit was defined for carbon-12, remember carbon-12 has 6 protons and 6 neutrons, so we said its atomic mass in atomic mass units is exactly 12. That's the only isotope where the atomic mass is exactly equal to the number of protons plus neutrons. For other elements, their exact measured atomic mass is slightly different from the number of protons plus neutrons. The atomic mass listed on the periodic table is a weighted average of the isotopes of each element. Now, what's meant by that? We'll start with carbon. Carbon has 15 known isotopes with neutron numbers ranging from 2 to 16. The most common one, of course, is carbon-12, which has 6 neutrons. Okay, and up to 2 decimal points, that makes up 98.93% relative abundance. So if you find carbon in the ground, 98.93%, it's going to be carbon-12. There's a 1.07% chance of finding carbon-13. So if we want to find the atomic mass on the periodic table, we take a weighted average, which basically takes the percentage. So carbon-12, here's 98.93% as a decimal, times the atomic mass, which is 12, plus 0.0107, that's the relative abundance of carbon-13. We add those together and we get 12.01. And that will be the atomic mass that you see on the periodic table.